So good morning, everyone. 9 o'clock again, and still everybody here. Very good. Sort of, right? So the topic of today will be stochastic backgrounds and how we hope to in the future maybe use stochastic backgrounds to learn about BSM physics. And for that, let me recap a couple of results, not necessarily from last lecture, but from the previous lecture, because these will be the things that we will need today. So first of all, you have the expression for the energy density of the gravitational waves, right, which we derived, which is given by the volume average or the time average over the time derivative squared of the gravitational wave. We can rewrite that, right? It has an integral expression where inside the integral you have the primordial information, right, the power spectrum at the time of sourcing or at the time of horizon reentry. And then we have the ratio of scale factors, which is the transfer function, which tells you the cosmological history. So how did the universe expand since the point in time that the gravitational waves were sourced? And then since we write this with this expression here to introduce this capital omega GW, which is the gravitational wave spectrum, and that will be the thing of use today. That will be kind of the thing that you predict from your favorite BSM model and then compare against experiments. We talked also a little bit about kind of what frequencies and what amplitudes to expect. So from the frequency side, for everything which is kind of in the post-inflationary universe, we saw that there's a relation between the frequency at which we observed the wave and the temperature at which it was sourced, such that higher frequencies correspond to earlier times in the universe. And then this I actually didn't have on the board, but I mentioned it in words, is that we already have one, even before doing gravitational wave experiments, we had one bound on the energy density in gravitational waves, and that is since they are radiation, they cannot kind of be more radiation than is compatible with the expansion history of our universe. And the way we measure this is typically in terms of extra neutrino species, delta N effective. Gravitational waves are not neutrinos, but it didn't matter at all that was neutrinos. It was just a master species. And so the bound is the delta N effective limit, which is about 0.1, the amount of photon density that we have. So that's the fraction of photons times the total energy density. That gives you about a number 10 to the minus 6, telling you that today, during radiation domination, gravitational waves could have been 10% of the total energy density. But then since the redshift of radiation, it means that today they can be at most about 10 to the minus 6 of the total energy density. And if you think kind of that your spectrum is somewhat broad in logarithmic frequency space, you can say, well, I can roughly convert this bound on the energy density on a bound on the amplitude of the spectrum. Okay, so now to today's topic, so to cosmological sources. So there's two different types of sources that one can discuss. And they can be either what I call transient or what I call continuous. So that should not be confused with something that we observe as a transient signal or a continuous signal, right? So a transient signal is something like a black hole merger, which happens once, we see it or we don't, and then it's gone, right? Whereas a continuous signal, depending on your definition of continuous, could be something like a stochastic background, or it could also be, say, a very early phase of an in-spiral where you see many rotations. But so here, these are all cosmological sources. So they're all continuous signals. But the question is if the time of the source, the duration of the source, if that was less than a Hubble time or more than a Hubble time. So what I call transient sources is some cosmological event, right, where the duration of the event has some time scale which is less than a Hubble time. And why that matters is that because that is the implicit assumption that actually went into deriving that formula, right? Because we said we sourced the waves at some time, right, where something happened. And that's kind of how we identified a frequency today with a temperature at the time that that event happened, right? So in this case, this directly applies. And what you expect is some sort of a peaked spectrum at a frequency that corresponds to the time of sourcing precisely to that relation. On the other hand, if you have a continuous source, right, which is the opposite, it means the duration is much, much longer than the Hubble time, then you're kind of continuously sourcing these waves. So in some sense, you can still apply this formula, but you have to apply it over and over again, right? Because you're sourcing and sourcing and sourcing and sourcing. And what that typically leads to is a spectrum that is present over a very long period of time. If this happens during radiation domination, you get something that is just scale invariant over many, many, many orders of magnitude in frequency. If it happens not during radiation domination, but something else, you need to take into account this ratio of scale factors, and you get a different power law, but you don't get a peak spectrum, right? You get something that is very extended over frequency. So extended but again, following that same relation, if you observe this extended spectrum, it will mean that the higher frequency part of the spectrum will correspond to the waves that you have sourced early on, and then the lower frequency part of that spectrum will correspond to the waves that you've sourced at later times. Okay, so with that, just as a background, wait. I got my order mixed up, but okay, well, whatever. So let me, okay, let's keep that as a background, and now let's do a little detour. So this just explains the type of signals that we want to be looking for, and I'll give you some examples of these types of signals later on in the lecture. But before we do that, let me tell you about the one missing experiment that we haven't talked about yet, which is pulsar timing arrays, because they have potentially already seen this type of a background. So pulsar timing arrays. So how do they work? So we are here on Earth, and we observe a pulsar, right? So that's a neutron star which is rotating. There's a beam, and this beam, kind of like a lighthouse, goes through space. And if we're lucky, we kind of see the flashes of this cosmic lighthouse, right? So there's some pulsars here and here, and they are emitting a very regular signal, which we then observe at Earth. And the idea is that if there's a gravitational wave passing between us and the pulsar, you can think of it in a proper detector frame that is kind of moves the distance between the pulsar and the Earth. And hence, there will be little time delays in the arrival time of these very regular pulses. Now, in practice, it's a bit of a mess because pulsars are astrophysics, and astrophysics is a mess. But we have, and if you just have one pulsar, you will not be able to say much, right? Because there's all sorts of things that could go wrong. But the idea is that you want many pulsars, and then you really look for a correlated signal that corresponds to the structure of the gravitational wave that correlates the time delays that you get from different pulsars.
I have a question. At some point when I was at a colloquium or something, someone said something about pulsar timing arrays. They said that the delay shift was not due to the distance to the pulsar changing, but something else to do with the pulsar itself being affected by the gravitational waves. Does that make any sense to you?
No. We completely. I'll go through the liberation in a moment. You'll see we completely neglect everything that has to do with the pulsar.
Okay.
It's a very local effect. So in some sense, it's okay. So what is true is that me saying, okay, this is we'll see when we go through the math, right?
Okay.
Then I think it will become clear. So what we measure is the time delay, right? Or the way they like to phrase it is in terms of redshift, which is the same thing, right? So redshift is the observable here, which is just the time derivative of the time delay along these arms. And this time delay you compute in exactly the same way, fundamentally, as you do for LIGO, right? Because fundamentally, this is kind of one arm of an interferometer, and you're asking the exact same question. The difference is that opposed to LIGO, we will be in the limit that the frequency is much larger than the inverse length, right? Whereas LIGO is the opposite limit. So we can do the exact same exercise as we did for LIGO, and we will get some expression for the redshift, which has this response function term, which now contains the geometry of your pulsars, where here this index alpha is the label of my pulsar. And we're going to evaluate this at Earth, which is coordinate 0. And now this guy here, so in principle, we computed exactly the same way as we computed it for LIGO. In practice, and this is now related to your question, in practice, since there's many wavelengths between us and the pulsar, what happens at the pulsar, we lose sensitivity to that, right? Just because there's kind of many oscillations. So really, we're just doing a local measurement in some volume around the Earth. So when we do that integral, we have the exponential. We have, we do this integration from 0 to L, and we drop the upper boundary. We drop what is called the pulsar term, because it's kind of, we lose sensitivity to it simply because of the many oscillations of the wave. So that's the only difference to the computation with LIGO, which makes this expression more nicer to write, which is why I write it explicitly. So here K, again, is the gravitational wave. P is the direction of the pulsar. Whoops. So this is beta. And this is the polarization tensor. And so this is for LIGO, it didn't even give you the explicit expression because it's a bit of a mess. It has the exponential, just turns into some sinc functions, and then you have to subtract one arm from the return trip and do the other arm. Here you only have a single direction, and you can drop the pulsar term, so it gives you a very simple expression. And so now you can compute this. And now what is your observable? Your observable, as I said, is you want to correlate the time delay from one arm with the time delay from the other arm. You can do an autocorrelation, right? So you can correlate signal alpha, this guy, Z alpha, but it'll be more interesting to actually do the cross correlation between two pulsars to check if that's consistent with a gravitational wave. So the observable that we're going to be looking at is the cross correlation Z alpha of t, Z beta of t. So now we can compute that, right? Because if we now assume, let's assume the simplest case, which is an unpolarized isotropic source, or isotropic stochastic gravitational wave background. So now you see that in that integral there is an integration d3k over all directions of the sky, right? But if I'm assuming an isotropic background, I can kind of flip, doing the integration over the sky and kind of doing the integration over the pulsars, summing over the pulsars is going to be the same thing. But the point is that if it's isotropic, I can just perform this integration over the gravitational wave over the whole sky, analytically. So let's do that. Okay. So we're going to use you remember the same relations, right? So we're going to get two of these guys. We assume for a second, but just for a second, an ensemble average, right? So then we get the correlator HH. We plug in our isotropic background, which means we plug in the delta D3K, delta lambda lambda prime. So we're left with one of the D3K integrals. The other one went away with the delta function. We're left with this correlator, right, which is essentially just a p lambda of k. Okay, sorry, I'm not actually, okay. I was fast in my words that I am in my notes, right? So what so I haven't actually plugged, I'm just writing the correlator, right? I haven't plugged it in yet, right? So we'll still have the delta function here. Then we have the second integral. Let me write it, then I try to understand what I was thinking when I wrote it. No, okay. I'm just splitting the integral into, I did do the correlator. I'm splitting the integral into just the part over the radial component and the part over the angular component, right? But we did already kill one of the D3Ks with the delta function. And then we have the two response functions, right? So from pulsar alpha and from pulsar beta. And now due to the delta function, they both have the same argument k. And now this thing will depend, of course, on alpha and beta, right? So it will depend on the position of the sky of these two pulses that we're looking at, alpha and beta. But it can only actually depend on the relative angle, right? Because there's nothing, since I'm assuming that my gravitational wave background is isotropic, there's nothing setting an absolute direction. Okay, so this thing can only depend on the relative angle gamma, which is the angle between p alpha and p beta. And this thing, if we evaluate it, so if we perform this integration, which is just literally an integration over this thing, right, which you can do by hand or plug into Mathematica, what you get is some function that I'm going to call mu gamma, function of this angle, index HD for Helling-Downs correlation, and the explicit expression is pretty simple, 1/4 over 12 cosine gamma plus 1/2, 1 minus cosine gamma, and then there's a log, 1 minus cosine gamma over 2. And this is the famous Helling-Downs correlation. Okay, so the statement is, if my background is isotropic, if I can do the ensemble average, right, then I can predict what I expect for the correlation of the time arrivals between two pulsars in the presence of the gravitational waves, just as a function of the angle between these waves, between these pulsars. Yeah?
Do you have any assumptions in here about the velocity at which these pulses are receding from us? Because we would expect like a longer time arrival just because
Right. So all this goes into your pulsar model.
Could you repeat the question?
Thanks. So the question was if there's an impact by the fact that the pulsar is receding from us, right? Because that will also impact the time delay. So when I say time delay, that's kind of the time delay with respect to the arrival time that my pulsar model predicts. The pulsar model is very complicated because it contains exactly what you say, right? I mean, the relative velocity of the pulsar, but also all sorts of things that you think you understand about the pulsar, noise components of the pulsar, the entire motion, for example, the motion of the Earth is not in the kind of the center of the galaxy, right? So the relative motion of the Earth, the observer, the telescope with respect to that pulsar, right? So all these things you have to take into account.
So in the equation for F, what is P in that equation?
It's the P, no, sorry, P is the direction to the pulsar. So P for pulsar, not P for momentum.
Okay.
Just confused what this quantity S alpha beta is. So it's a product of two redshifts.
Yes, it's a product of the two redshifts, and we should take this average, right? So this is it's.
So the T evolution is like so it's the redshifts function of time. In what sense?
In the sense, so this is not the redshift of the universe, right? This is the redshift of it's basically the time delays, right? It's just the time derivative of the time delays. So you're observing time delays, and now you're seeing kind of how these time delays evolve over time. Yeah.
I'm wondering where the delta function comes from.
That just so here we're taking the correlator, right, of h lambda, and then we have the relation in the isotropic universe, right? That's the power spectrum times the delta function in k times the delta function in lambda. Yeah.
Are you sensitive to the separation of the pulsars or the separation of the pulsars from the Earth?
Okay, so the question is, am I sensitive to the separation of the pulsars or the separation of the pulsars to the Earth? So here, this angle gamma is really just the opening angle between I observe this pulsar and I observe that pulsar. This we would in principle. So here I said we dropped in this integration, right? We dropped the second term, we dropped the pulsar term, and hence the distance of the pulsar actually dropped out, because we're assuming the pulsar is much further away than the wavelength of the gravitational wave. Otherwise, you would still have that term. Yes?
What's the sensitivity of like figuring out the difference between two wave? Like, because for LIGO we were talking about the width of the photon, so how does it
Right, we'll get there. So the question was about the sensitivity, right? We'll get there. So because we're not actually measuring the distance to the pulsar, right? So I'd rather quote the sensitivity in terms of directly the gravitational wave, right? So because that's the amplitude of the perturbation that is at the root of all this, right? But it doesn't one-to-one translate to the distance to the pulsar, because you have now many wavelengths between you and the pulsar, as opposed to LIGO, where all you need to do if you have a sensitivity to the gravitational wave means that the mirror changes by this number times length of the instrument. Yes?
Something that confused me a little bit. So you read this expression in terms of two particular pulsars and maybe data you collect about them.
Yeah.
And then you have this under bracket that it's the Hellingsdowns, but it wouldn't be for any two like specific pulsars, right? It would just be something. And then if you averaged over all of them, and then averaging over all of them.
Okay, so the question was, how do we go from two pulsars to many pulsars? Let me draw the plot. Okay. Right. So here so far, indeed, we've imagined a pulsar timing array where we just have two pulsars. Right. We can take any two pulsars. For any two pulsars, what we find is that the correlation is purely a function of the angle between these two pulsars. So now we collect data from many, many, many pulsars, right? And then we can draw, this S alpha beta, right? So the correlation as a function of gamma, right? That's not going to be a continuous curve, right? Because you have a finite set of pulsar, but you have the number of points here is number of pulsars squared, right? Nanograph has 60 pulsars, so that's actually a lot of points on this curve. And so the prediction from what we computed here is the Hellingsdowns curve, right? So you'll find everybody uses a different normalization, right? So my normalization, we start at 1/3, go from 0 to pi, and we're at something like this. So if your two pulsars are in the same direction, you get a maximal positive correlation. If they are at pi/2, meaning one pulsar here, one pulsar there, you expect anti-correlation, right? This is kind of the structure of the tensor structure of the gravitational wave. And if one is in front and one is behind, you expect, again, a positive correlation, but the correlation has gone down in magnitude because the pulsar separation has gotten very large.
So I guess, okay, so my follow-up question is this the curve you expect in our universe, or is this the curve you expect if you had a bunch of universes and averaged over all of them?
Yes, good point. And so the point was kind of, is this the actual, is this what I actually expect given that we only have one universe, right? No. So excellent. So this, well, yes and no, right? So this, so because what went into this curve, right? What went into this curve is that we assumed the stochastic background to be isotropic, right? Which, just as an aside, the other thing you could assume, which would give you the same result, is you could assume the pulsars to be distributed isotropically, right? Because then you could flip the integration from k to p by just doing a coordinate transformation, and you get the exact same result, right? So even if your source is completely localized, you just have a plane wave, but your pulsars, you have infinite many pulsars, you can just flip the integration, you get the same result. Okay, that's one assumption. The other assumption is exactly what you're referring to. We assume that we can take the ensemble average, right? Now, was that a good assumption? So let's first think in terms of time, right? So in terms of time, these guys have a frequency of 1/10 years, right? Because we're probing at the nanohertz range. Do we have many, many times 10 years of data? No, right? We have one or a few times 10 years of data. We don't have many, many times 10 years of data, right? So if we kind of think of this as separate samples in time, it's definitely not an ensemble average. Now, is it an ensemble average in the volume, right? Again, no, right? Because as we said, we're kind of only sensitive to basically within a single wavelength around Earth. Despite that the pulsar is further away, we can't access that, right? Because the wave oscillates, right? And we kind of can't get a handle on the pulsar. So again, right, the volume that we're measuring is basically the inverse of the wavelength. So again, this is not an ensemble average. And and that means that what you expect on this curve is some cosmic variance, because we only have one universe, right? So you expect actually that there's going to be some band here, and that your data points are going to be somewhere in this band, right? But not necessarily exactly on this curve. But never, I mean, maybe I exaggerated here I exaggerated the band a bit, right? I mean, you have a cosmic variance effect, right? But you do still definitely have the helix down structure. And this is precisely, I mean, then we had the observation, I mean, first in, first in 2020, pulsar timing arrays for the first time we're saying, okay, we see a noise source, which we think is not the pulsars. But at that time, they didn't have enough data to say if it was Helings Downs correlated or not, because you need to collect statistics. And then last year, they said, okay, we see something that looks like this, right? It still has big error bars, but it does follow the right trend, right? So it's not a 5 sigma detection, it's a, I think, 3 sigma-ish significance, right? But it is definitely compatible with it actually being gravitational waves. Now, the question is it primordial gravitational waves like we've been discussing today, or is it supermassive black hole mergers, which is an astrophysical explanation, right? And to be honest, astrophysics always wins, right? So mergers of supermassive black holes do give you kind of roughly the right amplitude, the right frequency range to explain that signal. So more study is needed to figure out what this actually is. But completely independently, if this holds up, this is the first detection of a stochastic background. So that's kind of an opportunity to kind of optimize our tools, learn about how to understand stochastic backgrounds, how to extract information, ask questions like what do we actually expect to measure, right? What does a deviation from this curve mean, right? I mean, apart from kind of statistical noise, right? Does it mean there's something in the data which is kind of beyond the vanilla model, or does it just mean, well, we just have one universe and tough luck? So all these questions are now the things that need to be addressed.
I have a question about the sensitivity are those? I don't. Those don't look like they should be normalized ones. If you have a longer array, it's going to be more sensitive to a narrower angle of incoming waves.
No, so the
More sensitive overall.
no, because if the pulsars are further away, so here you don't gain because we've pulsar, right? We've term that is kind of having there's an e to the 2 pi I x, and if you put x the pulsar location, that just drops out because that's a rapidly oscillating function. Because we
slowly oscillating.
Well, I mean, you have many oscillations, right? And hence you lose sensitivity. This is the same reason why is LISA or LIGO, why are they sensitive at 1 over the arm length, right? Why are they not sensitive to waves that are much shorter? And the reason they are not sensitive to waves that are much shorter is that you have many oscillations of the wave within the arm length, and hence you lose sensitivity.
Doesn't the sensitivity still increase for the longer waves?
Yeah, but on the long, no, because the problem is if you make the waves longer, is you run out of observation time, right? Because then they have a period of longer than 10 years. And since we only have 10 years of data, we can't see, like a wavelength that has a period of 100 years would just seem like a constant, right? And a constant just looks like a gauge artifact, right? I mean, we can't measure a constant. We can only measure things that actually move within the observation time. Yes?
Yeah, so how would you estimate the size of the cosmic variance?
Right, okay. So question is, how would I estimate the size of the cosmic variance? So what you do is you compute, you literally compute the variance of this guy, right? So you take the square, the average of the square and the square of the average, and you subtract the two. So you can do it analytically. Under these kind of simple assumptions, that the background is completely isotropic and so on. Okay. Any other questions? Okay. So now let me get back to. So as I said, I mean, I think the most logical explanation for this is mergers of supermassive black holes, which, by the way, is already super exciting, right? Because you learn something about the last parsec problem. Supermassive black holes means these are the black holes at the center of galaxies, right? So we're talking about galaxies colliding, right? So these are all extragalactic events. Astrophysicists extremely happy, right? They can learn many things, right? Also, you do learn a lot about kind of the environment close to this black hole, right? So once you have your astrophysics under control, if you have your astrophysics under control, right, for sure you can talk again about dark matter and all these things, right? Similar to the merger story that we were talking about yesterday. But now what I want to talk about today is like true cosmological sources, right? Which may or may not have something to do with this observation, but is something that we can look for with this type of experiment, but also with next generation ground-based experiment, and also with LISA. So let's start with the transient sources. And the first one that I want to mention is one that we know exists, but it might be very small. It's the cosmic gravitational microwave background. Right, so the idea here is you have some primordial plasma and this will, we know, emit photons, right, which at some point become the CMB. Now that same plasma will also simply thermally emit gravitational waves. Now the CMB photons decouple at 1 electron volt, right? The gravitational waves, or the gravitons, they decouple at the Planck scale. Since the universe never had the temperature of the Planck scale, it means they just decouple instantaneously. It's a very UV-dominated process, so whatever was the highest temperature of the universe will set the scale for this process. So let's get some gravitational waves, and this is then the cosmic gravitational wave background. So what we expect is that this will have the same frequency dependence as the CMB, right? So it will be peaked in the radio range because it's simply the primordial plasma of the universe redshifted to today. And it will be, however, suppressed compared to the CMB by a factor of the reheating temperature, so the maximal temperature of the universe, with respect to the Planck mass. And this number is much smaller than 1. Okay, so this is something which is there, but it's out of range of any foreseeable detection, because A, it's in the radio range, right, where we don't have any detectors, and B, it's at an amplitude that is kind of even way below the n-effective bound, right? The n-effective bound would have a factor 0.1 here. But at least that's a standard model one. So I wanted to show it. After that, we go beyond the standard model. Yes?
Can you maybe just quickly explain where the suppression factor comes from? So I understand that it's suppressed, but like, how do you get exactly this?
Right, so it has to be some power of reheating temperature over Planck mass, because that's just the decoupling temperature, right? So they want to decouple, like if the CMB decouples at an EV, right, that it can decouple at an EV. This guy, to do the same thing as the CMB, it would want to decouple at the Planck scale. But the universe never had the temperature of the Planck scale, right? So you can kind of compute the thermal production rate, and you'll see that the thermal production rate is suppressed because you're not at the temperature where you can produce these guys without penalty.
What is the theoretical upper bound of TDE?
So there's a bound from inflation, right? So from inflation, from not observing tensor modes in a CMB, you have an upper bound on the energy scale of inflation. And that upper bound on the energy scale of inflation, if you now assume instantaneous reheating, you can translate into a temperature, and that's about 10 to the 16 GeV. So assuming we're just around, assuming that tensor B modes are just around the corner, this is 2 orders of magnitude, right? But who knows where the tensor B modes are, right?
When you say that the universe never had the temperature of the Planck scale, you mean after the heating?
Right. So the question was, what kind of? Well, it's essentially the same question, I think. Like, what is the upper bound on the reheating temperature?
Not really. I mean, so my question is, couldn't the universe have a temperature of the Planck scale before inflation?
Ah, yeah, but before inflation, everything gets inflated away.
Okay.
Yes, yes.
Okay.
So post-inflation, yes. Okay, so a more optimistic scenario are first-order phase transitions. Okay, so the idea is you have some potential function of some scalar field, and you have a false vacuum and a true vacuum, and as the universe cools down, at some point you tunnel from the false vacuum into the true vacuum. Now, we have phase transitions in the standard model. Unfortunately, none of them meet this criteria, right? So none of them, neither the QCD nor the electroweak phase transition in the standard model are first order, but I'm sure you all know some BSM models that can accomplish this, right? You extend the scalar sector of the electroweak symmetry breaking, and you can somewhat easily find yourself in this type of a scenario. And in this case, there's various. So I mean, you have phase transition, so you have these bubbles of true vacuum forming. The bubbles expand, they collide. The whole plasma is sloshing around. It's a very violent process. So you get a whole range of possible sources for gravitational waves. You get gravitational waves when these bubbles collide. You get gravitational waves from the turbulence effects in the plasma. You get gravitational waves from the sound waves, which are sloshing around in the plasma. And depending on the parameters, any one of these could be the dominant source. So we won't go into the details, but just to give you an idea, let's estimate this omega gravitational wave, right? For the frequency, it's the estimate that we had on the very left, right? So for the frequency, it means if we have something like the electroweak phase transition, this will end up in the LISA band. Now for the amplitude, we're going to introduce beta, which is the typical time scale of the phase transition. So gamma here is the nucleation rate of the bubbles. Right, and then 1 over beta is just the duration of the phase transition. And then we're going to introduce alpha, which is the ratio of the difference between the vacua and the ambient energy density, right? So this thing here is rho vac. And now in terms of these two parameters, so in any BSM model, you would start with a Lagrangian and do some computations, and you would compute the nucleation rate, you would compute your potential, and you can, from your Lagrangian, you can derive these two parameters. And now in terms of these two parameters, we can estimate the gravitational wave spectrum, because if we start again from our favorite wave equation, right? Let me put, so again, we want the anisotropic part. I don't have good notation for this. Let me put T tilde to indicate the anisotropic part. So just parametrically, right, this box will turn into a beta squared, right, just from the time derivative. And then the gravitational wave, right, the energy density we saw is h dot squared divided by 32 pi g. So h dot, we can use again this relation, right? You put one factor of beta on this side, and then what you have on the left-hand side is h dot, just parametrically. So you'll get 8 pi g, this t tilde parameter, divided by beta squared. And this anisotropic part of the energy momentum tensor, we're going to expand as, yeah, I know you can't see. I'll put it up in a second. Or maybe I can write it here. We just expand T tilde over the vacuum energy over the total energy times the total energy. And this parameter here we call kappa. This parameter here we identify as alpha. And so now we can put everything together, and we get that gravitational wave is a factor rho gamma over rho tot, right? So this is just the radiation energy density today, 10 to the minus 5. We get Hubble divided by beta squared. This is the Hubble at the time of formation. And then we get kappa alpha squared. And these things, so this was the duration in units of the Hubble time, right? So I mean, this has to be a causal process. So this is to be smaller than 1. But it doesn't necessarily have to be much smaller than 1. And the same here, right? These parameters have to be smaller than 1. But they don't necessarily have to be much smaller than 1. What you see is that you can actually get energy densities which even exceed the BBN limit of 10 to the minus 6. Right? That simply means that that part of the parameter space is excluded by observation. But you can, with these models, reasonably easily get relatively strong signals. So if, for comparison, the sensitivity of LIGO is 10 to minus 8 or so now in omega. LISA will go down to 10 to minus 13. Pulsar timing arrays are even better, 10 to minus, well, are similar, 10 to minus 12, I think, at the moment. So these are potentially very large signals. And what they look like, right, is just, since it's a signal, a transient source that just happens at one point in time, right, it's just going to be some peak spectrum with power laws here that you can compute depending on what is your dominant source of emission, and the amplitude that we computed here, and the frequency that is still written there. Okay, any questions about this? Yes?
Here it's the formula is only valid for the gravitational production during the formation of the, during the formation of the bubble, not everything is happening after like collision of bubbles.
Well, I mean, it's all still pretty much roughly within a Hubble time.
Okay.
Right? Because, okay, you start forming the bubbles start merging, then you have all this turbulent dynamics, but it doesn't really last more than a Hubble time.
But the parametric dependence might be different. Like, so probably not be as sensitive as.
Right. I mean, what I'm doing here is something extremely oversimplified, right? I mean, there's hundreds of people, I would say, working on nailing down, maybe some of you also, right, nailing down the exact prediction of what we expect for the spectrum given a Lagrangian, right? This is really just a very rough parametric thing. But it also kind of shows you, even for other sources, like roughly what you need to do, right? I mean, if you want a strong source, it does somehow need to have energy density that is comparable to the energy density of the universe at that time, right? If you have some source whose energy density is tiny compared to the ambient energy density, you're going to have additional suppression factors on top of that, right? And it's going to be correspondingly hard to see. And you also want order 1 anisotropies. Otherwise, again, you have suppression factors. OK, any other questions? While you have time, while I wipe the board. So the reference that I just erased is a review on cosmological sources, which is a lot more information than what I'm giving today. So, well, this is a terrible job. I'll wipe this board. Okay, and then the last topic for today, continuous sources. Right, so these are sources that last for much more than a Hubble time. So what could that be? The probably most commonly discussed example is inflation. So why am I saying inflation is a continuous source? Well, inflation has just the way it has vacuum scalar perturbations, which end up being the temperature fluctuation of the CMB. There's also vacuum tensor perturbations, which get generated during inflation, get stretched to classical scales, freeze out, right, as we saw, just stay sitting there on superhorizon scales, nothing happens, they wait patiently until it's time to re-enter the horizon, then they start oscillating, and then they are present today in the universe as gravitational waves. Now, the trouble with these guys is they are small, right? So we have an upper bound from the fact that we haven't seen them in the CMB, which is an upper bound on the energy density during inflation. And that upper bound means that if we stay with single field slow roll inflation, not in my lifetime, I would say, right? So it's a very nice, it's a beautiful prediction of single field slow roll inflation, but it's too small. So I mean, we're still hoping. We could see them in the CMB at any moment, right? There's a free parameter. There's an observational bound, right? CMB totally has discovery space. But these direct detection experiments, I would say too small. But you can have more exotic models of inflation, right? So you can have models of inflation where you have during inflation some additional source of perturbations. So if you have some additional source during inflation, and this is, I mean, it's not trivial, right? Because you need something that is a sufficiently strong source, because inflation tends to dilute everything away exponentially. So what you need is a source that is exponentially fast, producing fluctuations. One example of something that do this is what goes under the name of axion inflation. So if an axion coupled to the field strength tensor of some abelian gauge field, that type of a model gives you a tachyon instability in these gauge fields, so you get an exponentially strong production of gauge fields. That gives you an exponentially growing anisotropic energy momentum tensor, and that gives you a significant additional classical source of tensor perturbations during inflation. That can give you something that you can see, right? So that's something that LIGO is putting bounds, PTA is putting bounds, LISA will be putting bounds. The other thing that you can do in inflation in order to actually get a signal that you can hope to see is what goes in the name of second order gravitational waves. So the idea is you can do this in single field, but not slow roll. So what happens is you can have a model where you very, very much enhance the scalar perturbations, right? So you have some phase of ultra slow roll or something where you're kind of piling up scalar perturbations at the same scale a lot. And so you get a huge amount of scalar perturbations. And then at second order, you can have two scalar perturbations going into a gravitational wave, right? And that can also be a source of gravitational waves from inflation that you could potentially see. Of course, the model has to be somewhat exotic, right? Because you need some phase. I mean, you need to really enhance your scalar power spectrum from 10 to minus 9, where it is at the CMB scales, to 10 to minus 2 or something like that, right? So your vanilla chaotic inflation model is not going to do this for you. So what you can do is if you have a very strongly enhanced PZ, so scalar power spectrum, because, for example, you have a slow roll parameter which goes to 0, right? Your field is going very, very slow, right? Then since this guy scales as 1 over the speed of your inflaton field, it blows up. And then you can estimate that the gravitational waves that you'll get from this guy will be some number, right, which you have to compute, times amplitude of these scalar perturbations. Let me put it here, they call it P, let me call it P again, over 0.01. Again, the radiation energy density, which is 10 to minus 5, with the same logic, and some function, let me just call it S, which describes just the detail of your spectrum, which is roughly order 1. And this number here in front is 10 to minus 9. Right, so that tells you if you manage to blow up these guys from 10 to minus 9, where they are at the CMB scale, to about 10 to minus 2, then you could see them with pulsar timing arrays. Right, this is roughly the sensitivity of pulsar timing arrays. Now, if you blow up the scalar power spectrum to that magnitude, you could also be starting to produce primordial black holes. Right, so depending on if you like that or don't, that's either a good thing or a bad thing, right? But it's also kind of a way to probe these types of models.
So, yeah, you enhance this scalar perturbations to 10 to the minus 2, and then you somehow need to kind of dilute them such that at CMB scale, like Yeah, 10 to the minus 9. How difficult is this to integrate this kind of?
Right. So the way you do it is you have an inflation model. So what you want to actually construct is that you have p zeta as a function of frequency or distance. If you here have the CMB, you want it to be very small here, right? And then you want it to do something like this, right? Or maybe like this or something, right? And this is 7 orders of magnitude, right? So how difficult it is to engineer, I think, depends on. I'm recorded, right? Depends on your taste for aesthetic for a nice model, right? It can be done, right? It can be done. It requires a lot of fine tuning.
Future CMB experiments, I mean, I guess in order to see such large enhancement, you would just need to resolve CMB at smaller scales to see these larger, because the idea is like, yeah, we could kind of constrain more and more as we have much better data.
Yeah, but here's 60 e-folds, right? So it's true. So for pulsar timing arrays, it's true, right? Because pulsar timing arrays are not so far away from the CMB, right? So we have the actual CMB anisotropy measurements, right? That's the direct measurement. But then we also have the measurements of Moody distortions, right, which push a little bit further. But I think we're not going to be able to get much further than that, right? Because these are really, this is a logarithmic scale, right? So we're not going to push the CMB scales by orders of magnitude. But it is true that if we, I mean, currently there's some bounds, right, from CMB, and then here from some Moody distortion bound, right? And if they go down further, you kind of have to get an even bigger growth here. And for pulsar timing arrays, you are going to run out of space to do it. For LISA or LIGO, you have enough room on the x-axis that you can still construct models. But I'll be honest with you that these models are basically constructed for the purpose of generating a signal, right? Be it either in primordial black holes or be it in gravitational waves, and not something that really supernaturally falls out of your theory. Any questions? Yes?
What is S in that equation?
So questions, what is S in this equation? So S is a source term that parameterizes this shape of the spectrum, right? So I've normalized it in a way that is roughly order 1, but it gives you the detailed shape of the spectrum, right? But at the peak, it's order 1. Okay, so the last source that I want to talk about is cosmic strings. Right, so we talked about phase transitions. And in some of these phase transitions, you could, in addition to the signal that we talked about, you could generate topological defects. Or even, it doesn't have to be a first order phase transition, right? And just can also be second order phase transition or crossover. In principle, you can generate topological defects. So what are cosmological defects? So imagine in the simplest case, imagine a U1, global U1. So you have some kind of Mexican hat potential, and as the temperature of the universe goes down, your field will fall down into the rim. And in different points in the universe, different patches, it could fall down into different patches of this, different directions of this rim. So what that means is that if I look at my universe in some patches of the causal horizon at that point, right, so the Hubble parameter at that point, some patches, and now I have some directions here for this wave. I could have a configuration where here in the middle I have generated myself a topological obstruction. So there's no way, if I have a configuration like this, there's no way that just with infinitesimal movements of these arrows, I can make them all align, right? They would want to align, right? Because then you have less energy in the system, but they cannot align if they happen to fall in a way that kind of gave you a net winding number, and that you're left with something in the middle, where here in the middle you really have the false vacuum energy restored, and you can't get rid of this object by just small transformations. And so this is a 1D picture, and if you think of this as a 3D picture, you get a string which is coming out of the board, right? So you get some one-dimensional object. So in three-dimensional space, this thing will turn into some one-dimensional object. Yes?
So because if the U1 is perfectly symmetric, there's no like tiny breaking like there is with some accents, shouldn't we erase the line boundaries and just keep the strings? Because the arrow can't rotate continuously around the string, there won't be.
So the only thing that we're left with is here's the string, right? There's nothing else.
Yeah. But the picture there doesn't make it look like that. So we should erase the lines.
Yeah, that's just a drawing to give you an idea. I just want to indicate the size of the Hubble patches, right? Nothing happens on this line, right? That's just to give you an idea of the scale of the Hubble patch. So now, once we have these strings, they will evolve, right? And you can have a string and another string, they can intersect, right? So they will do then, to minimize energy, they will then do something like this. Because recall, there's a lot of energy on the string, right? Because on the string, you've restored the false vacuum. And also the string could do something like this, that it kind of folds back on itself, and that will lead to the chopping off of a loop. And now you can have both. I mean, if it were a perfect loop, right, or a perfect straight line string, you would not get gravitational waves. But the thing is that the way you've generated this network and the way kind of all this dynamics happens, these are not perfect lines and circles, right? They have a lot of substructure, and they are oscillating, they are vibrating, right? So you have vibrations from the loop, which are emitting gravitational waves with all the harmonic modes of the loop. And you have vibrations of the long string, which are also sending out gravitational waves. Turns out that the loops are more important, right? So it turns out that the name of the game is to be able to follow the string dynamics, compute the loop population function, understand the substructure on the loops, and then compute the gravitational waves emitted from these loops. And this is a process which just goes on and on and on, right? You can show that these strings, they reach a so-called scaling regime where the fraction of energy in the string network is always a constant fraction of the total energy. And that remains true in radiation domination and matter domination all the time, right? So you just kind of constantly have this network. We expect, with this, you'd expect to have order 1 strings even today in our local universe, I mean, in our Hubble patch. So if we get very lucky, well, I don't know if that's lucky, right? But if it were happen to be close by, we could see it directly, right? That's very unlikely. It's probably far away, right? But the loops, this big population of loops could be emitting gravitational waves over the entire cosmic history, and that's the type of thing that you would want to look for. Yes?
You mentioned on global. What happens if we gauge it?
Haha.
Cosmic strings or gauge it?
Right. Yeah. So the question is, what happens if we gauge the U1? So we still get cosmic strings. We then call them local cosmic strings. Basically, the entire explanation still holds. It's a bit less confusing because a bit more confusing because gauge symmetries, right? But mathematically, you can show everything still goes true. Actually, it's even better for gravitational waves because here you can emit radiation, massless radiation, into gravitational waves and into the Lambo-Goldson boson. If you have a local string, you don't have the massless scalar degree of freedom. So the only way that is not mass suppressed to emit radiation is into gravitational waves. So that's actually, local strings are more efficient in emitting gravitational waves. Yes?
Is there a bound on the symmetry breaking scale from the fact that we haven't observed it?
Right, so the question is there a bound on the symmetry breaking scale from the fact that we haven't observed it? Yes, right? And the interesting point is that here, the more energy you have in the string, the energy on the string is directly related to the energy here of the symmetry breaking. And the more energy you have, meaning the higher is your symmetry breaking scale, the larger is the signal that you get. Right? So you're probing the symmetry breaking from above, as opposed to all collider experiments and nearly everything else that we have that always probes from below. And the current bound is around the gut scale. Right? The current strongest bound is from LIGO, and it's around the gut scale.
So is this assuming that this field doesn't interact with like other fields in standard model particles? Because otherwise it could just dump this energy by reactions to other particles, right? And you wouldn't have this concentration of energy that we're talking about.
Right. So so actually it will, like, for example, people have computed this for, say, the B minus L string, right? So the breaking of the B minus L, which does have couplings to other particles. But the way these couplings typically work is that from the string, you first have to generate particles of the Higgs field or the gauge field associated with this breaking scale, right? But since this is spontaneously broken, these particles have a mass of the order of that breaking scale. So they are very heavy, right? So even though these particles then couple to lighter particles, right, you first need to generate quanta of
so
the Higgs and the gauge fields.
Potential does not decay because you still generate a massive particle.
Yes. Yes.
Yes. The same scale.
Yeah. So you kind of exactly. So you have to, in order to go to particles, you have to at least virtually go to a heavy particle, and that's why the gravitational wave suppression is still very important. And okay, so I said this for U1, right? More generally, the statement is that if you break from some group G to some group H, then you get cosmic strings if the first homotopy class of the quotient group is non-trivial. Okay, it's not just U1s, right? But U1 is the only thing I can draw. And then we can see what we get for the spectrum.
Do we get it for electroweak symmetry breaking then?
Haha. So compute, right? No, you don't.
Can you repeat that question?
Yes. So the question was an important one, right? Which is if we get it for the electroweak symmetry breaking, and we don't. So if you compute SU2 cross U1 into U1, you actually.
You want to be group is 3.
Yeah. Yeah. So in the standard model, so what you get in the electroweak phase, and there's actually something very interesting. You get dumbbells. So you get kind of temporarily, you get little strings from the U1 that you're breaking with little monopoles at the end from the SU2 that you're breaking, but they're not stable. So they only last for a short time, really, during the electroweak phase transition, but not stable. Okay, so let's put some experiments, right? So we have PTA, right? I said it about 10 to the minus 9 currently. We have LIGO. This is not going to be to scale. This is better. 10 to I think it's better. I think it's better. Wow. Okay, maybe I'm just not going to put an axis, right? Relative scaling should be correct. And then we have Lisa. So it's roughly like that. So okay, LIGO is about 10 to minus 8. Yeah, I think this is about 10 to minus 10. Okay, anyway, then I know the x-axis, right? So this is nanohertz, this is millihertz, right? And this is 100 hertz. So roughly, kind of, this is what we expect. Actually, I think, sorry. I think what I'm, let me draw this better. So this is future pulsar timing array, right? And then we have existing pulsar timing array, right? And now it makes sense that this is kind of 10 to minus 9, and Lisa actually comes down a bit further.
It's Lisa and LIGO. Could you label them?
Yes. So that's roughly kind of what we have at the moment. And CMB would be over here, and it would be pretty string and bound.
The main improvement for PTA would just be the number of pulsars that can kind of check, or is it also an existing model?
And the telescope, right? So this line down here would be SKA, right? So more pulsars helps a lot, right? Because it goes with the number of pulsars squared, but also better telescopes helps, right? So for example, now in China, they now have this fast telescope where they can see a lot of pulsars, but also like if you can resolve very well the pulsars, if you can spectroscopically resolve all these little pulses, you can get a lot more information than if, like, in particular compared to the data that we have that is partly 40 years old.
Does it really go like the number of pulsars squared? Because I feel like the additional correlators are correlated to the other correlators because there's just a fixed set of them.
Right, so the question is, do PTAs really scale with the number of pulsars squared? Because it's not completely independent. So it does go. So for an isotropic stochastic background, okay, it depends where are your pulsars, right? The thing is, the pulsars are in a galaxy, right? And the galaxy is not isotropically around us, right? But if we neglect that, right, then it really is a number of, for the, not necessarily for the detection just of some red noise, but for measuring Helling-Downs correlation, it does go as number of pulsars squared. I mean, this is kind of as long as you're statistics dominated, right? Then, of course, as long as you're just trying to beat down the noise, right? Then at some point, of course, that won't be the case anymore. Okay, and now our cosmic string signal will look something like this. Right, and then at some point it will stop. So this is some roughly scale invariant part during radiation domination. These are the gravitational waves emitted at very early times. This turnover is because radiation domination is a stop at some point, right? It could also actually go like that. We don't know. Right, let's just cut. And here, these are the gravitational waves generated during matter domination. And these, at some point, are the gravitational waves generated very recently, and we just kind of run out of time to generate them, right? And so you see, and this would now be a spectrum, let's say around the gut scale, right? So for some symmetry breaking scale around the gut scale. And now as you decrease this energy, so as you go down here, what would happen is that this spectrum moves to the right and it moves down, right? So you will get something like this. And so by doing these measurements, we can put upper bounds on the symmetry breaking, on the scale, the temperature of the universe, where we can have a symmetry breaking process that leads to these types of defects. Yeah, so the PTA bound is currently on 10 to the 14 GeV for the symmetry breaking scale, which is pretty stringent. It's basically already killing the gut scale, right? I would say the gut scale is around 10 to the 15, 10 to the 16, right? So roughly we're now down to 10 to the 14, at least in the simplest models. I should say that there's significant uncertainty in the calculation of this spectrum. Very significant uncertainty, right? And what I'm showing here is the more optimistic calculation that is leading to the bigger signal. So caveat, right? Okay, I think that's all that I have. Happy to take any more questions.
Sure. How much can that curve turn up pre-radiation domination, and would that fall into like kilometer
Good. So the question was, how far does this curve go up, right? And does it can it be detected by the holometer, which is an interferometer at higher scales. So it goes up, actually, if the reheating is matter dominated, right? Then we get here the same slope, which is f squared that we get here. And we get it for the duration of reheating. However, we still have to respect the BBN bound, right? So there's simply an observational constraint from the BBN bound, right, which is then somewhere here, right, 10 to minus 6. So here we have BBN, right? So whatever model you construct, beta has to come down, or beta kind of that puts the limit on the reading temperature. Otherwise, you're going to be in trouble, right? And the holometer does not get close to the BBN bound, unfortunately. But I should also mention that, I mean, here I've stopped the plot at 100 Hertz. Thinking about what you can do over here is something I'm personally extremely excited about, because that's where the really early universe is, right? That's where the completely unknown physics is, that's where preheating is, that's where we have lots of ideas where we could generate signals with high amplitudes, but we need to come up with new ideas for detectors.
All right, I think let's defer further